Hello everyone, and welcome to Chapter 12. So now we're going to look at the evolution of stars. So Chapter 11 was all about the formation of stars. This chapter will be about how they form once they're, or how they evolve once they actually form. And then the next chapter is star death. So we're looking at the middle. But let's move on. We got a couple slides that talk about that. So here's our learning objectives. These are always a good outline of what we're going to do. And then, so here's just a little bit of a recap. So like we said, Chapter 11 was star formation. So stars form by condensing from, that should be dense, condensing from dense clouds in the interstellar medium. So we have planets and stars and a bunch of stuff, and then we have all this interstellar medium around here that we use through everything. And that interstellar medium is really what gives birth to a star. And then once a star is born, it continues to grow, obviously just like children do. But a star is going to reach stability or its maximum height, or whatever analogy you want to use. It's going to reach that stability by fusing hydrogen into helium within the core of that star. So like we saw with the sun, we have that real hot spot or core in it, and it emanates out. So we have the photosphere, chromosphere, and some of it we can't really see. We see this part out there that where we look at the rays, but that's the that's the atmosphere of the star. So every star has an atmosphere. We started by understanding stars. We started our understanding of stars by studying the sun, and every star has that atmosphere, that relationship, just like the sun does. So generically, for all stars, they reach their stability by continuing that nuclear process here, and that nuclear process is fusing hydrogen into helium in the core. And that process, that fusion process, releases enough energy to counteract gravity. So gravity in the core right here is pulling everything inward. So if gravity won, it would collapse. It would collapse in on itself. But the energy right here, the energy within the core is enough that it's counteracting, it's pushing outward. So gravity is going to create enough pressure to close in on itself. But the energy by this fusion is greater than gravity, so it continues to push outward. That energy is radiating outward. So the energy generated at the core radiates away at the photosphere. So it's radiating, everything's radiating this way. So we're emanating out, and once that stops, then it collapses in on itself. But again, that energy generated at the core makes its way to the surface, and then it's radiated away. And when it gets to the surface, it creates that color. We get to see the shining star. So stellar evolution, we just looked at the birth. Stellar evolution is right in the middle. So we have a star is born. So we have that star is born and a star dies. But right in the middle is that stellar evolution. And that's what we're looking at in this chapter. So we looked at the main sequence stars in earlier chapters, and main sequence stars are basically that's all the stars that fall on that Hertzsprung-Russell diagram. So that's your color diagram. You basically see them go this way, where you have luminosity versus temperature on our axis, and we see this Hertzsprung-Russell diagram. Not always as curved like that. Sometimes it can be a flat line. Sometimes it can be really pronounced. Sometimes it's just a lot less pronounced like that. But at any rate, the Hertzsprung-Russell diagram shows a whole bunch of stars on that spectrum of luminosity versus temperature, and they're typically dwarf stars. They're really small, and the sun is actually about midway between on that diagram. But basically, we look at that Hertzsprung-Russell diagram, and we see all these. That's the main sequence of stars. All the dwarf stars that we're observing, and But in general, any star, whether it's on the main sequence or not, we cannot look into the interior of the star. That energy or temperature or luminosity is so bright, we'd be blinded if we did. And even with great technology, our really good telescopes, the Hubble telescope, all of them, they still can't see into the inside of a star. So that's where our hypothesis comes in. We've looked at hypotheses in the earlier lectures. So in understanding the interior of stars and that evolution of stars, a lot of hypotheses are made, and then the hypothesis has to be tested. But when we're talking about something that we can never actually see the interior of, there's a lot of limits to that testing. So we can't be totally certain about our observations of the about what we're saying about the interior of stars. So the limits to the hypothesis testing deal with the stellar interiors. We can't see them, but we're going to make conclusions about the interior by observing the exterior of the stars. And then the stellar evolution in general, there's limits to testing our theories about, or our hypotheses about the evolution. So we're going to always look at a snapshot. We're going to just look at that Hertzsprung-Russell or mean sequence of stars for a snapshot of clusters, perhaps, or a snapshot of stars, and observe basically what's going on in that cluster. So despite these limits, the astronomers have learned a lot about how stars are born, how they evolve, and how they die. Another word about this snapshot is that with this star life, born, evolving, and dying, rarely, very rarely, does that ever happen. Rarely does that sequence happen in the life of a human astronomer. So these take extremely long times for stars to be born and die. So it's generations of astronomers that have to do the studying. So when you do any kind of experiment, whether it's scientific or not, when you use that scientific method, you always want to document everything you do, and your record of observations is what gets passed on to the next generation for them to be able to reproduce what you did and build upon that. So one thing that evolved, because we can't look directly into the interior of a star, the astronomers come up with models about that stellar evolution. And there's four different types or four areas of physics that come in very handy. So hydrostatic equilibrium is one of them, and that's really basically the weight on each layer of a star is balanced by the pressure in that layer. So it's not caving in. Weight, if let's go to one definition here. Your weight is equal to your mass times the pull of gravity. So what you get on the scale, the number you get on the scale, that's your mass. It's not actually your weight. So scale is how much of a substance you have. So how much are you made up of? And then gravity, it pulls down on you, or pulls towards the core. So if this is the Earth, right here, gravity is pulling you towards the center of the Earth. That's why you could stand over here and not fall off the Earth, because that gravitational attraction is pulling you towards the core. Same thing with down here. You're going to stay on the Earth there, and gravity pulls you to the center. So everywhere on the Earth that you are, gravity is holding you onto the Earth. It's holding you onto the ground. You're not going to fall to the core, because there's an amount of pressure and heat pushing outward that keeps the Earth from exploding. But in general, we want to look at gravity is what's pulling you towards the center. So the weight, so hydrostatic equilibrium is the weight on each layer of the Earth, or each layer of the stars, is balanced by the pressure in that layer, the pressure, that outward pressure there. So you're not caving in. The Earth and the stars and everything aren't caving in on themselves when they're in equilibrium. You got that perfect balance between weight and pressure. And then energy transport, we did look at that, where energy moves from hot to cool regions, and it does so by three means: radiation, convection, or conduction. And then the new term terms now are mass conservation and energy conservation. So mass conservation is when the total mass equals the sum of the masses in all the layers. So you have this star here, and let's just put some layers around it right there. So actually, if I should draw that a little bigger and change my color. So we have this real big star right here, and here's the core. Change my color there. So we'll put a layer right there around a core, and we'll put the outermost layer, no matter how oddly shaped it may be, and another layer right there. So in each of those layers, the mass, this mass has to be equal to the sum. The total mass has to equal the mass at every layer. So we have a mass out here, a mass here, and a mass here, and we can keep getting real small all the way down. So all those masses have to sum up, and it also has to be uniform. We can't have any gap in there. So there can't be a hole. So there cannot be a hole, and there also can't be a gap, like a little indentation like that either. So the mass gets uniformly spread around. We also can't have a bump on it either. So mass gets uniformly spread around, and so all the mass, when we go through here, no matter where we go through, all that mass in each area sums up. So our total mass equals the mass at ring 1 plus the mass at ring 2, mass at ring 3, etc. And then energy conservation, that luminosity, that brightness, the same thing there. That equals the sum of the energy generated per second in every layer. So same concept as mass. Every layer has a layer of brightness, and all that the luminosity of every layer is going to sum up to equal the total luminosity. And it's the energy generated per second too. So a whole lot of energy gets generated in that short amount of time. So our model of the sun, from these four, and all our stars really, but so from those four laws, we can come up where astronomers can use all their equations here, their radius, their mass, luminosity equations, temperature equations, and they can come up with a lot of numbers that really describe the surface or describe the star. So here in this case, we're looking at the sun, and we have the energy radiating out from the core, and then it can create that energy radiating outward when it's cooler out here. We get this little convection cycle going on here, but we still get heat coming out. And all of that, whether it's radiation or convection or conduction, the astronomers are able to use all these math equations here to come up with like the ratio of a star to the sun, the temperature from that star, its density, its mass in relation to the sun, and its luminosity in relation to the sun. So all those numbers come together to give you a good feel, to give the astronomer a good feel for what's going on in that star and what's going on in particular in the middle and how that star is evolving. So how do we know? Again, we know that by math models. So mathematical models are a lot of equations designed to mimic or predict the behavior of objects and processes the scientists want to study. So for astronomy, the math models the math models of stars are to help astronomers understand what's inside the stars. It's geared towards helping astronomers understand that evolution from birth to death and what exactly is happening inside that star. So what happens inside that star is important to the growth of the star and its evolution from birth to death. So when they stop, so for instance, when we talked about hydrogen being a component of a star, making up stars, and when hydrogen is zero, when there's no hydrogen within that star, the star can't survive. So that's kind of like the aging process. You lose collagen in your skin. Here in a star, you lose hydrogen, and once that's gone, the star doesn't exist or can't survive anymore. So that's part of the evolutionary process, is understanding how much hydrogen is left. So the scientific models are only as good as assumptions that go into them, and that's true in general of any scientific experiment. The models are difficult, again, to test against reality, but they do give us a lot of observable things like the main sequence. This is our luminosity. And then the mass of the luminosity, the mass of the star in relation to the luminosity. We get a good feel there, and that's what we saw over here. That's what we saw in this by these numbers here. You got your mass. You have your mass right here and your luminosity. So the relationship of the two of them together gives a lot of good data to study, or helps understand what's happening with a star. And then observed numbers. When you look at these numbers, you can predict what's a giant and what's a supergiant. And then the shape of the star clusters in that Hertzsprung-Russell. Is it real pronounced? Does it drop off this way, or is it a straight line? So you get to see where death is, where birth is, and everything in between, by understanding the numbers there. So maximum masses of main sequence stars. Here's one example of a supernova. So the more massive cloud fragments, they break into smaller pieces during star formation, and very massive stars lose a lot of mass in strong stellar winds. And this is actually a stellar wind right here. This is the star right there. That's in the center of this picture, and and the wind from this star right here, fast blowing wind here, is it created this little bubble effect. So this is a nebula often referred to as Thor's helmet. So if you kind of think of that old Viking helmet right here, that's what it looks like. A little bit. I don't remember if that's a little bit of a beard right there. Anything's coming, but at any rate, the star right at the center of that nebula is actually what caused this solar wind. And the solar wind, it blew this bubble, or created this bubble effect. So we have the star in the middle, and then we have the bubble out here. And then of course some of the gas being given off. So the bubble is about 30 light years across, and it created this molecular cloud that was called, or the fast-moving wind created that bubble, or a fast-moving cloud, and it was all created from that bright massive star near the bubble center. So the star producing the wind and exciting the nebula is an extremely hot giant star, and it's thought to be in a brief pre-supernova evolutionary state, and that's because of the blue-green color that indicates the evolutionary state that it's in. So whenever there's a star that has a mass, a fraction of the sun, so when a star's mass, so we'll have the mass of a star is less than this 0.08 of the mass of the sun, then the stellar progenitors, it is a stellar progenitor. It doesn't get hot enough to ignite that thermonuclear fusion. And so all the fusion that occurs in here, that gives you a yellow. So that would make all this yellow here. If we had a lot of that fusion going on to give off a brighter color, a real bright, or make it very luminous, then in this case here, this star is not hot enough to ignite that thermonuclear fusion, and consequently, it's called a brown dwarf. And so a real brown dwarf, though, is right down here, and it's a lot smaller. So this star right here, in this case here, it's still actually, it's giving off a lot more heat, and it's going to eventually shrink to that point. So a brown dwarf, they're difficult to find because they're not very luminous. They're not very bright. And their luminosity is so low that it makes it difficult to detect them with the naked eye. and not obviously with the naked eye, but what you would need, or what astronomers would need, is a really high powered telescope. And even with a high powered telescope, they're very difficult to find. So what the astronomers use is the infrared type of telescope, and that helps see. It helps detect energy in the infrared region, so it's not energy in the visible region. So, and notice that this is an artist's concept, because we can't take a visual picture of a brown dwarf. We can't see it with a telescope, or anything that would create a picture that the normal eye could understand or interpret. Rather, we see an infrared image, and based on that infrared image, we know that's emitting in the red. So that's where, but not bright red, not well, it is right here a little. That's more of an orangey color, but it's mostly. It's mostly in that rust-colored region, so it's not red hot, and it's obviously not white hot either. It's far from it. So it's a very dimly colored star, or very dim star in general. So the main sequence stars, they're the dwarfs, and they're the really bright ones, and they exist by converting hydrogen. This is hydrogen. Into helium. So when there's no hydrogen, we no longer have a stable star, and it's going to explode or cave in on itself. So we see here newly formed stars. Newly formed stars here begin life at the lower edge of the main sequence. So pretty much like lower edge of the main sequence is where they begin their life. And then stars exhaust the last of the hydrogen in the cores as they leave that main sequence. So as they're moving away from the main sequence, they've exhausted all of their hydrogen, and we see the sun. We see the present day sun is moved a little bit, so it's been about 10 billion years, right there. So newly formed stars begin life at the lower edge of the main sequence, and it just happens to be the top part here, and then so that's the lower edge, and then and it's the lower edge because of our temperature range right there. No, I'm sorry, I said that backwards. Obviously, right here is the lower edge, and so 10 billion years ago is what this should say. This is 10 billion years ago, and 10 million years ago. So here's where the newly formed star begins, right there. So we had our initial sun down here, and we moved up a little bit right there. So you see that little bubble. It looks like a little snowman on it. That's what we're looking at right there. So the sun on that Hertzsprung-Russell diagram hasn't really moved that far physically. And that's why it makes it so difficult to observe a star from birth through its evolution to death. When we figure 10 billion years ago is the first glimpse of the sun, and then the present sun right in there. So we still have a long time before we see the sun actually die. So a star's life, or a lifetime, is really decided, and this is an approximation. That means approximate. It's a little tilde sign, and it's an approximate as opposed to equal. So the star's lifetime is approximately equal to the energy reservoir divided by its luminosity. So and luminosity of the sun is always our baseline right there. So massive stars have short lives. So we see that the more massive the star, the more massive, the smaller, or the shorter it lives. So the less number of years that it has to live. 10 to the 6 is smaller than 10 to the 9. So these are going to live a lot longer than this guy up here. So and then they're not massive at all. So we see that here. We see a very massive star right here, and this one's closest to the sun. The sun equals 1, and this is just slightly bigger than the sun. So it's about how long the sun's going to be, 9 times 10 to 9 years. So again, the key thing here is massive stars have short lives. And so after the so when a star lives on that Hertzsprung-Russell main sequence, the helium core, along with the hydrogen burning shell, produces more energy than needed for the pressures to support. So you wind up with an expansion. You're getting you used to have this nice and tight, densely area, so you end up with an expansion. And so these hydrogen shell right here, it starts right there and it moves outward, and you're starting to get that big expansion. And as you expand, though, you see some cooling of the outer layers of the star, and consequently you get what's called a red giant. So that's where you see the red hot star, the really hot one there now. So our sun is expanding, and eventually our sun is going to expand beyond the Earth's orbit. And right here we still show it on the main sequence. But eventually the sun's going to become a giant star. It's going to go from a dwarf. Everything on this Hertzsprung-Russell scale is a dwarf star, and the sun's still on there, so the sun's still a dwarf, but it's going to expand and it's going to become a giant. And then the ones up here that are expanding become supergiants. So less massive stars evolve into the giant region, and that's what the sun is. It's not that massive. And the ones that are more massive than the sun, so 3 times the mass of the sun, and then the ones here that are 5 times the mass of the sun. This is 5 times the mass of the sun, 15 times the mass of the sun. They all become supergiants. So the sun's going to become a giant star, and the ones down here will become either a giant star or stay as a brown dwarf. So stars, so we talked about hypothesizing and theorizing and building models, and how we understand what happens on the interior of a star, and how that helps us understand the evolution of a star. But another way to understand stellar evolution is to look at a star cluster, not just that Hertzsprung-Russell cluster, but a cluster of stars that are grouped so close to each other that you can reasonably expect them to have been born around the same time, or born of the same cloud. And so they're roughly the same age, approximately the same age. And again, you can gauge that by measuring how far away they are. They're light years away. So when they're all really close in distance from the Earth, you can pretty much guess that they all formed at the same time. So that cluster, when you put that cluster on a Hertzsprung-Russell diagram, they still stay as a cluster, but now instead of looking at the entire diagram, you're only looking at what's happening to your cluster that you're interested in. So your cluster gets put on this main sequence somewhere, and it means everything above here has already died, and everything down here is still a brown dwarf. They're too faint to see. So we still have the brown dwarf, so they haven't evolved yet. So these are different stars down here, and then these are the ones that have died off. So a star cluster, the M3 Hertzsprung-Russell diagram, the evolution of a globular cluster star, we end up seeing the helium shell fusion, and the core. So we have some stars getting off the Hertzsprung-Russell diagram, but then moving back and then getting off for good. So in that case here, you get this star cluster around here. But you still see all the stars grouped together. You still see your overall cluster on this Hertzsprung-Russell diagram. So to estimate the age of that, this is actually taken from your text, all of it is, but you can go and look at this diagram here, the pages here, and you'll see that the older the cluster is, the lower it'll turn off the lower it'll turn off of that main sequence on the Hertzsprung-Russell. So MS right here is the main sequence. So the main sequence then, the older the cluster is, the lower it's going to turn off of that Hertzsprung-Russell diagram. So here's your main sequence. The Hertzsprung-Russell diagram always gives you the main sequence. So you got your main sequence right there. And if you're turning off down, like really low down here, that's an old one. But then if your star cluster is pretty much right on that full range, you got a lot of young evolutionary and old stars all grouped in there. But then the lower it turns off of the Hertzsprung-Russell diagram, that would mean that it's the older it is. So right here is a pretty old one. And only the lower mass stars are remaining on the sequence here, and that's the ones up there. But you're actually falling, or the ones right here. But you're actually getting everything off the cloud or off the sequence. Here's the upper main sequence stars, and they've all died already. And but you can actually go ahead through and read the other examples in your text. And then another way of understanding the evolution of a star is through variable stars. So some stars, so we looked at clusters of stars, and then we've looked at models of stars too. So there are two ways, and the third way is variable stars, and that's also the third way of showing evidence of stellar evolution. So some stars are intrinsically bright variations, not caused by eclipsing in a binary system. Actually, they just have variations in their brightness, and you can measure that, and as the brightness as gets dimmer and dimmer, or brighter and brighter, you can tell where it is on that Hertzsprung-Russell diagram. You can pretty much put it somewhere on that spectrum. So a misconception that probably should be obvious by now is that stars are constant. A misconception is that I'm sorry, let me rephrase that. So a misconception that should be obvious by now is that stars are not constant. So we should understand, or actually what I'm trying to say is that this myth that stars are constant, we should have debunked that. By now it should be obvious that stars are not constant. So people often think that a star is constant and that it doesn't change. So the misconception is that when you look at a star, whether you're looking at the sun or whatever star you're looking at, that it looked like that from the dawn of time, and that it's going to look like that forever. Well, what we've just shown is that that's not true. We learned in the last chapter that stars are born. We learned in this chapter that they evolve, and we'll learn in the next chapter that they die. So stars do change, and stars are not constant. So we just debunked the misconception or the perception that stars are constant and unchanging. The truth is that stellar models show stars slowly evolve as they consume their fuel, and the evidence is the Hertzsprung-Russell diagrams can confirm it, and they show that slow changing structure. So the variability period of the Cepheid variable is correlated with luminosity. So when you have that variation in luminosity, you can assign a number to it, and that's what you see right here. And you can see all these changes of Cepheids right here, and you can study those different changes. They correlate with luminosity and changes in that luminosity. And then a pulsating variable is for some combinations of radius and temperatures, a star can maintain a periodic oscillation. And that corresponds to locations in the instability strip. So we're starting to see a star move from a stable phase into the unstable phase and leading on to death. And the Cepheids pulsate with radius changes of about 5 to 10%. So that little bit of degradation right there is enough to cause a pulsating variable or a pulsating star, and that's going to change its radius and temperature, where it's going to fluctuate in those areas. So any questions, of course, please reach out.